Hi. So first, I'd like to thank the speakers for the organizers for this wonderful event and for inviting me. And I'm going to talk about quantum money and some of its extensions, and that's why and friend there. So before we start, just two comments. First, there's going to be quite a few references. At the very end, there will be a long list of references, so just scribble down the one you're interested in. The details will appear at the very end. And that's it, I guess. Okay, so, and please feel free to ask me questions. We have some extra time, so it's totally fine. Don't feel bad about it. What's the idea behind quantum money? So in 1968 or 69, Stephen Wisner invented this concept, and that was how he presented his paper. His motivation was simply money that it is physically impossible to counterfeit. Now, as you can imagine, it was 1969. This was before the no cloning theorem, before people even started to think about quantum physics as something that can store information, and it was pretty hard to convince people of the plausibility of his idea. It took, again, roughly 15 years to get his work published. And we'll see why this is so, why this is indeed plausible. So what are the properties that we want from quantum money? So the first thing is that it should be easy for the bank to generate the money. It should be easy to verify the money. Next, we'll see what exactly do we mean verification, who can verify it. And it should be impossible or hard to forge money by anyone other than the bank. Now, classically, this is impossible to achieve, right? Classical material or classical information, such as the bills in our pockets or coins in our pockets, can, in principle at least, be copied, like atom by atom or whatever way you want to look at it. Another approach that was used for money was gold, which is supposed to be scarce. But again, there is no law of nature which says that gold has to be scarce, right? In fact, gold was synthesized, I mean, in the early of the 20th century. So we would like to have something in which, like, we have a law of nature which helps us in achieving this goal, and not just, in practice for some reason which might or might not hold. And indeed, in the quantum setting, we have the no cloning theorem, and therefore qubits cannot be copied, and at least, in some settings, and therefore we hope to achieve this goal. So, as I said a minute ago, there are two important variants of quantum money. One is, they are called private and public quantum money. They differ in the sense that in the private setting, only the bank can verify the money using its own secret key. And in the public setting, there is a public key issued by the bank, and everyone can verify this, the money using that public key. So in some sense, private quantum money is more similar to a bus ticket, where the bus company issues these tickets, and they are the only one interested in verifying it. Whereas public quantum money is more similar to the coins and bills we have in our pockets, where we can transact with each other without the bank interference or involvement. The good news about private quantum money is that it's easier to implement. It does not require a universal quantum computer, whereas in all the public schemes that we have, we do need a quantum computer. Again, for one advantage of the private scheme is that there are quantum schemes for private quantum money which are information theoretically secure, whereas all the, and this is actually proved that you have to have computational assumptions, at least you need computational assumptions for public quantum money. Okay, so how do we formalize these notions? So both private and quantum money and public quantum money consist of 3 algorithms. The first is the key generation algorithm, which just take a security parameter, which we'll see later what it means, this security parameter, and outputs a secret key. Then using the secret key, there's an efficient way to prepare the quantum money state. And verify, which takes the secret key and an alleged quantum state and either accepts or rejects. And of course, we require that the correctness property that if that verify should accept valid quantum money, right? The quantum money that was prepared using this process. And here is public quantum money, and the differences are highlighted, so it would be easier for you. So here, keygen outputs both a secret key and a public key. Mint works as before, just outputs some quantum money state. And this time, verify uses the public key in order to verify the money states. And the correctness property is as before. It just should accept valid money. So how do we define security? So I'll do it again in a series of attempts. It's not as simple as you might imagine. So the first attempt is that you know, if the adversary, I'm talking here about public quantum money, although the differences for secret private quantum money aren't that different. So the adversary in the public setting gets the public key and the security parameter, and he's allowed to work in polynomial time in that security parameter. So the bigger the security parameter is, the harder it is for the adversary to break your scheme. That's why it's useful. And the probability that the adversary would be able to pass this verification test when he doesn't have any money should be negligible. So this means that the adversary cannot create money from thin air, right? And negligible means that it decreases faster than 1 over, that it's a function that decreases faster than 1 over polynomial. So, and again, it means that there is no way to print money from thin air, but perhaps there is a way to, say, make $2 out of $1, which again would be problematic, right? So this is our second attempt. So here, verify squared here just means apply verification to these 2 copies that the adversary tries to make. And again, using here the adversary is given 1 quantum money state, and he should not be able to produce 2 valid quantum money states. Perhaps it could, but then the probability should be negligible. So to generalize this, we simply say that, okay, the adversary is given n quantum money states, and he should not be able to prepare n+1 quantum money states. And for me, it seems kind of reminding a variant of a thermodynamic law, right? There is some quantity that cannot increase, right? So perhaps it should motivate the physicist here. And now, this sounds like, I think it sounds like a good definition. In fact, it was the common definition for quite some time. And I'd like to let you ponder for a minute, is it good enough? And try to come up with problems with this definition. If anyone has ideas, I'll be happy to hear them. So I'll give a hint. So indeed, you cannot create more money, but that's not the only problem that could happen. That's at least that's the problem. The only problem I know with this definition.
If you have extreme good luck and create one quantum banknote, then you shouldn't be able to produce many copies of it.
Actually, but if you're extremely lucky, I think you would, right? By guessing the secret key, you would be able to do so.
Yeah, information could leak from the verification process.
Good. So we'll also discuss this, how to, and indeed it's problematic. You need to be extremely careful about it. But I'll give another problem. So the idea is that an attacker might be able to change the money so that it will fail verification the second time, right? No one said that no one excluded that option. Okay, so only the second time you'll verify it, it will fail. Right? The security definition did not force us not to have this property, and therefore perhaps it is possible to do it. And let's see, of course, how this is problematic. It's kind of, I'm giving a simple example here. So you have two competing stores. Store 1 attacks store 2. So store 1 has some money. The store tweaks that money so that it will pass verification once, but will fail verification the second time. And indeed, this is not excluded. Now, store 1 buys merchandise from store 2 using that tweaked money. And then, again, it goes to the second store. The store tries to verify the money. The money is it passes verification the first time. And now, the second store perhaps gives, merchandise for the first store, and then the first store didn't lose anything from that transaction. And then when store 2 goes to buy something using the money that was received, it is considered as, it doesn't pass verification, and therefore it lost all the money from that transaction. So this seems like a problem, right? And to fix this, we suggested to add the requirement that the verification is a projection, and therefore if you run it once, it will continue to pass and you don't have to worry about it. But I guess what I want to stress here is that these things are far from being closed, right? It's not that obvious what kind of attacks can happen, and we need to all think about these aspects. Okay.
Something else that could happen is that the money is valid and it passes verification, but the merchant just says, oh, it's no good. And in the process destroys it, so that the buyer has no recourse. Saying, oh, it was good, but now it's gone, so what can you do? This doesn't quite happen with paper money. If you tell me that it's no good, then I take it back, we call the police, and it's still there for verification.
Indeed. Yeah, good question. I don't know if there's a way to resolve it. You know what? I'll actually present a way to resolve it, and we can discuss it. If I didn't plan to do it, so please remind me to do so if I forget. So I'll start with presenting Wisner's original scheme, which uses 4 1-qubit states. So each one of these, we have 4 states, each consist of 1 qubit. These are now called BB84 states, but actually Wisner's is the one who first used these 4 states as far as I know. The 0 state, the 1 state, the plus state, which is just a uniform superposition over 0 plus 1, and the minus state, which is 1 over square root of 2, 0 minus 1. Okay? And for each, so imagine that the bank wants to print money. or mint money. And then for each serial number, what the bank does is prepare, adds the serial number I to the first a classical part, which is called the serial number I, and a quantum money state of the form, say, minus tensor 1, tensor 1, tensor plus, tensor minus, tensor 0. Just a uniform state of that sort. And the bank also maintains a classical database that contains that classical description of these qubits, right? So just a classical bit string of the same sort, right? Minus 1, 1, plus, minus 0 for the ith entry. But again, this is a classical object, not a quantum one. And verification is done by projecting onto the correct state. So for example, here, in this example, the bank measures the first qubit in the Hadamard basis, and if the result isn't minus, it is simply rejected. And then he moves on to measure the second qubit. If the result isn't 1 in the standard basis, then it rejects it, and so on and so forth. So he either measures in the Hadamard basis or in the classical basis. Sorry. Okay, so the scheme provides exponential information theoretic security, and Molina, Vidic, and Watrous proved the following theorem, that if you have one quantum money state, the probability of you winning this challenge of creating another quantum money state is 3/4 to the n. And another feature that some quantum money schemes have is classical verifiability. So here, before verification was simply an algorithm, whereas for classically verifiable quantum money, verification is done via a classical interactive protocol between the bank and the user. So there are quite a few constructions that achieve this, starting by Gavinsky, but I'll present the one by Molina, Vidic, and Watrous simply because it is very close to Wisner's scheme. So in their scheme, to verify, the bank asks the user to measure each one of the qubits in the standard basis or the Hadamard basis uniformly at random, but independently of the way that the money was created, right? So just to measure in a random basis each one of the qubits. And the bank then compares the results only on the places in which it really, the money was created that way. And they show that also that provides exponential security. Okay. So far, we considered schemes in which do not involve noise, right? If one of the results was faulty, we kind of saw the money as invalid. And of course, for reasons related to noise, this is ridiculous, right? Of course, some of the outcomes would be wrong. Pastowski et al. Gave a variant to Wisner's scheme, very close to it, but that can tolerate an error rate, even in the honest case, of 15% and proved security. Wisner also argued that there is that it should tolerate noise, but you know, it was kind of a hand-wavy physicist kind of an argument, which is of course valid, but it's just here we have a formal proof for this fact. Another issue that was raised is how to keep the database small. Now, I'm happy that Charlie is here. I'm not sure if you'll agree with my interpretation, but I'll present it in modern terms. And Wisner, isn't it? Okay, so yeah. So I guess both of you are here. So instead of keeping a large database that contains all the numbers in your, in this long bit strings, you keep one secret key, let's call it K, and use a random number, pseudo-random number, pseudo-random function fk of I in order to prepare the ith, like to generate your ith bill. And this, of course, requires computational assumptions, and that is it.
Just for historical amusement, based on my memory, this is precisely what I came up with when Charlie attacked me in the ocean. When Charlie first told me about these quantum money, for those who know the history of quantum crypto, and the history goes on that by the time we swam back ashore, we had our first paper written. That was that paper, and specifically the idea I had still in the water was this one.
But you certainly didn't use the word like pseudo-random function. I'm not even sure if it was. But do you accept this interpretation that really what we are looking for is a pseudo-random function? Great.
Yeah, they had not been invented yet.
But to be honest, I'm not even sure whether this is proven anywhere. I haven't seen a proof that this scheme as presented.
Not of that sort. That sort had not yet been invented. A keyed pseudo-random function with provable properties from. Yeah. Sure.
Okay. Okay. So now I'm going to ask a kind of. Something that might sound silly. Why do we actually need at least private quantum money? In what sense is it better? So I argue that we asked for the property that no one can, if I give you like a quantum money state or just one money, you shouldn't be able to copy it. But this is an overkill. In some sense, what we're really interested in solving is something called the double spending problem. The double spending problem simply means that you use your same coin twice and get, 2 coffees with $1. And this is way simpler to achieve if you allow your bank to maintain a database. In some sense, not in a very different way than we use credit cards. So here's my alternative classical private money. So money is, think about like a coupon or something, which just contains a very long classical bit string. And the bank keeps all these bit strings in his database, only the unused ones. And verification is done by checking whether this bit string appears in the database. And if it does, the bank simply removes that bit string from the database, right? And now, suppose you come, if you try to buy 2 coffees, the first time you will succeed, but then the second time you come with that number, you won't, right? So what's the advantage of quantum money here? So again, if anyone has ideas, I'll be happy to hear them, because I don't have very good reasons.
Thank you. Well, yeah, the obvious reason is that to do what you just said requires online instantaneous communication with the bank, whereas a good, be it quantum or classical, but a good money scheme must be verifiable offline.
So like public quantum money?
Like banknotes, like regular banknotes. Or
sorry? Like?
Regular banknotes. You don't have to call the bank to verify that.
Great.
Or the DigiCash stuff. It's just as good. But But the bad thing about what you just said was the requirement to be online with the bank each time you make a transaction.
So, but private money, again, you need to transact. So I'm specifically comparing private quantum money to this scheme. So as you said, it would be better to have public quantum money in which we can verify ourselves, but that's a different story, and I agree with you. But what's specifically comparing it to private quantum money?
Oh, I'm sorry. Yeah, I'm sorry. Yes.
So I think one advantage of private quantum money over the scheme you propose is if I trust somebody at a certain point, then I can accept money from them without verifying it. So then I know that if I don't trust them at a later point in time, I don't have a problem.
Oh, actually, it's a good point. So if they weren't malicious at that point, but why can't they physically just burn their coupon? Like give you their coupon, or if they copy it, make sure that they destroy it at that point in time. If you trust them, this would be good enough, isn't it? You're saying it would be too hard for them to destroy? Okay.
Yeah, if it has been on a disk or something, then it's hard to destroy.
They could keep a backup copy of it if it was not on it.
Good. Actually, yeah, that's an advantage even for the classical.
Backup copy means that if they become dishonest, they can later double spend.
I see. Okay. Okay, so I guess all of these points are valid. But the one that at least I thought of is no, actually, I think it was explicitly mentioned in Dmitry Gavinsky's paper, that there's no need to maintain a database. And perhaps, why is this relevant? So suppose you have several branches, even on perhaps different planets, you can imagine, they do not need to communicate. They can work on their own without ever communicating with each other after minting has stopped.
Excuse me. For the original Wiesner solution, you need a database, which tells you for each.
Sure. So I mean, like
in a dynamic database, perhaps.
I mean the one with you don't need to maintain that database. In the meaning, you don't need to update it. Or if you want to use just the one with the pseudo-random function, and then you just have something which is reasonable to, Okay. And to be honest, if we're honest about it, these days, like, two branches can communicate with each other, and then none of this is important. And since communication is so ubiquitous, so I don't see it as a really selling point that stands for giving a serious advantage to quantum money. So another feature that was studied is related to anonymity, and perhaps this could be an advantage for quantum money compared to the previous scheme the classical scheme that I talked about. And this is very similar to coins versus bills, and Mosca and Stebila coined the term quantum coins, I guess. And the difference is, what's the difference between bills and coins? Like, bills have serial numbers, and these serial numbers can be used to track people, and indeed it is used to track people in some cases. We can discuss whether it's a good thing or a bad thing, but it does happen. And the nice property about coins is that they are indistinguishable from each other, and therefore provide this anonymity. And in Mosca and Stebila's scheme, all the quantum money states are exactly the same, and therefore provide anonymity in a similar manner that coins do. And in that last reference, they use a slightly different approach to get anonymity. Well, when I'm short on time, okay, I'll go a little bit faster. So next we're going to discuss public quantum money. So just to recap, the main difference here is that for verification, you only need the public key, and therefore everyone can verify the quantum money state. And another advantage of the scheme is it is better in terms of privacy, right? The bank is not involved in your transaction. The bank is not aware of what just happened, only the two people involved. I guess another advantage is that there's no way to do a denial of service attack, right? Everyone has the bank's public key, and there's no way to attack the bank again do a denial of service attack. There are three candidate constructions. This scheme by Aronson Cristiano seems to be the most promising at the moment. I'll present the others later, but I'm saying it ahead of time. So for that scheme, we need some background, and I'll try to give quite a few details on this construction. So suppose A is a subspace of f2 to the 2n, and this is a subspace of dimension n. And I'll just give an example. So f2 to the 4 consists of this vectors 0, 0, 0, 0, 0, 0, 0, 1, up to 1, 1, 1, 1. And addition in f2 to the 4 is done pointwise, right? So here we have an example. So you simply, take that bit, XOR it with that bit and get a 1. You XOR this bit and that bit and get a 0. XOR this bit and that bit and get a 1. 0 XOR 0 gets a 0. And so this is how you do addition in f2 to the 4. So this is like our vector space. And an example for a subspace of dimension 2 could be this one, right? And this is a subspace. If you add 0, 1, 1, 0 with itself, it's this one. You can check that this is close to addition. And multiplication is just 0 and 1, so it's easy. And indeed, this is of dimension 2, right? These two vectors span the entire space. Subspace, sorry. So the first fact that we'll use is that given a basis for A, right? A basis for A is just n elements, which has a concise description, even though, remember that a subspace of dimension n contains 2 to the n vectors. So the vector space itself is huge, but it has a compact description. So given that compact description, a basis, there is an efficient way to prepare this quantum money state, which is the uniform superposition over all the elements. And this is going to be like an important state, this ket A. And for this previous example, this is just uniform superposition over these four elements that we had before. And eventually, this is going to be the quantum money state, right? This uniform superposition over some subspace. We need another definition, A dual. This is the set of all elements from this vector space that the inner product with all the elements in A is 0. And the second fact that we'll need is that if you apply the Hadamard transform to that state A, you get the state A dual. So this is another subspace, and here A dual is just the uniform superposition over that subspace. This is kind of not too hard to show. And now we'll define this projection to be the projection over all the elements in that subspace. So notice that this is pi A is a projection of dimension 2 to the n, right? We have 2 to the n elements, and each one of these is a rank 1 projection, and they're all orthogonal. So this is a rank 2 to the n projection. And similar for pi A dual. And the interesting fact, which is a very nice exercise, I think, is the following. If you apply this projection onto A, then apply the Hadamard transform on these qubits, apply pi A dual, and Hadamard tensor n again, you get a projection onto our, well, this A, which is our quantum money state, right? So this gives you a way to, if you have oracle access to A and A dual, you get a way, using here, they appear here, then you get a way to verify our quantum money state, right? So we have a way to verify our money, but we need some other properties, right? The main property that is hard to show usually is the unforgeability. So that's what we're going to talk now. So how do we show this is hard to forge? So Aronson and Cristiano show that if we have these membership oracles for A and A dual, Grover's algorithm, right, it's pretty easy to see that using Grover's algorithm just to A, you can generate this quantum money state using, or this uniform superposition using this many steps for these reasons. And, but more importantly, this is asymptotically tight. There's nothing better that you can do. Another property that if you're given one copy of A, then the success probability of the optimal cloner is exponentially small also. But more importantly, we have two kind of resources here, right? Here we have these oracles, and we can argue using query complexity. And here we have a state, and we can use like arguments for like no cloning arguments. And Aronson and Cristiano call this the computational no cloning theorem, which combine these two resources. You're given both one copy of A and membership oracles to these to the subspace, and they prove that you need at least exponentially many queries to clone this state. And if you remember, like in one of in the second, I think, attempt for our security definition, we said that you cannot clone, given one copy, you cannot create two copies. So this is precisely what they show here. And in fact, they also show a way to take a construction for which has only this property and strengthen it to a full-blown quantum money scheme. This is so this weak definition is called the mini scheme, and they show a general way to make it a full scheme. Okay, so of course, one concern is how do we get rid of this oracle? So the original construction used polynomial to hide the subspace, but by now this scheme is completely broken. Since I don't have so much time, I won't explain exactly what happens, but the bottom line is that recently Jandry gave a, I think, beautiful proof, security proof, and now we have a provably secure public quantum money scheme based on general assumptions. So this is something we never had before. We had some of the schemes that we had were this is kind of new. This is the first construction which achieves this based on general assumptions. So I'll now give another construction by Farhi et al. I'll only mention it. It's based on beautiful knot theory. Unfortunately, I won't have time to get into the details, but it has a very interesting feature which I would like to mention, that even a corrupt mint cannot generate two quantum money states with the same serial number. And that has a very nice implication that it provides a publicly verifiable way for the people to know what is the total amount of what is the money supply, how many coins are totally available. By just publishing the list of all these serial numbers, and when you're verifying, you just check that this appears in that list. Okay, so some important attack vectors for quantum money, and this is something you definitely should. This specific attack is extremely important. You should keep in mind if you ever want to design your quantum money state. Quantum money scheme. So the question is, what can we learn about our quantum money state, especially in a public scheme? Here we need to, for technical reasons, we need to further assume that the verification is rank 1 projection onto the money state. And for Wisner's scheme and Aronson Cristiano's scheme and several other schemes, it has this property. So this seems like a reasonable assumption. And that this is a public scheme in which like the state is returned to you can, if whatever comes out of the verification procedure, whether it failed or not, this post-quantum measurement state pops out. You can take out your quantum money state back. So if you have that assumptions, then you can measure you can evaluate the expectation value of your quantum money state with respect to any two-outcome measurement AMP, okay, without destroying the state, right? So usually when you do a measurement, you can gain statistic if you have many copies, but here you have only one copy, and yet you can get this very good approximation of this value. And in particular, you can do local tomography for your quantum money state, and therefore, something like Wisner's scheme, in which our quantum money state is a tensor product state, simply cannot work for a public money scheme. And perhaps surprisingly, we can do even better in the sense that even if, so you can imagine that if the money is invalid, you throw it away and that's it, it's gone. You don't return it to the owner. But you do give money back if it was valid, right? This seems like reasonable. But it turns out this doesn't work. You have something, you can basically get the same kind of result as was presented here, but only by, you only check that the bank, that the money is valid. It always tell you yes, it's valid. And yet you learn something. You learn this expectation. This is kind of surprising, at least it was for me. It uses Leviatman's and Aronov's concept called protective measurements, and we showed how to use it for attacking Wisner's scheme when money is returned, valid money is returned, and invalid money is destroyed for Wisner's scheme. And I guess the lesson is that if you want to return valid money, if someone goes to the bank and gives a valid money, the bank has to issue a new money and give it back. The bills cannot be reused. It's like one-time bills. Okay, so some experimental demonstrations, and there were a few others, but I'll mention only two. The first one by Bozio et al. Showed an experimental setup very close to QKD, and in this work by Bartkiewicz, they showed some attacks on Wisner's scheme, but unfortunately, I'm not aware of any experimental results that demonstrated storage. And this requires, of course, quantum memory, and this is technically, of course, a challenge. So in I'm going to very briefly mention a few extensions of quantum money, since I don't have too much time. So I think this is very exciting, this development. This is which deals with randomness. So as we've seen, like in Tomavi Dick's talk and many other talks, suppose I give you a number 10001101, you cannot tell whether I used this function to generate it or really gave you a random number, right? Classically, this cannot be done. But fortunately, in the quantum case, this can be done using a concept called recent construction called quantum lightning. So it could be viewed as quantum money on steroids. It's just a quantum money state, and now it's R, but usually we think of it as a serial number. Now we think of it as some random bit string. But now this quantum money state certifies that R was random. Right? The goals are entirely flipped, right? Before we use the serial number to somehow verify the money. Here, the money certifies that this R is random. Or in what sense is it random? It means that R was generated using a process that contains lots of mean entropy. That's basically what he shows. And the idea is that, for creating this quantum money state, you create this huge superposition and measure part of it. And, if you repeat this process, you'll eventually get a different result. And the verification basically checks that you follow these procedures, that you first generated a huge superposition and then measured it. And therefore, it contains lots of randomness. And the details are kind of complicated, but I think this is the main idea. Okay, so I guess there are some caveats. This was very like the previous version was broken. It was just updated a few days ago. There wasn't any peer-reviewed. So and it uses a very non-standard assumption. So I cannot say how secure it is, but nevertheless I think it's a very interesting work. Last comment. Notice that usually for certified randomness, we're interested in knowing that the adversary does not know R. This is does not guarantee it isn't guaranteed here. It's more similar to a randomness beacon where we just know that these are random, right? We cannot say that no one else knows about it. So I have to do it. I cannot. I can't do it. I have to mention this result. So what is quantum copy protection? Again, this is a beautiful idea, similar to quantum money. So this is a compiler which takes one program, like a classical program, and outputs a quantum state. And the quantum state can be used to run this program or circuit, but it is impossible to create two copies of this program or to pirate that program. So that's why it's called copy protection. So two different people cannot evaluate the program on random inputs without communicating. So of course you can lend your friend this program, but that's it. You cannot pirate it. And we only have kind of construction for point functions. So I'll skip that, and I'll skip that, unfortunately. Okay, so some of these constructions, especially these dispensable backdoors.
You have lots of time. You have still like 30 minutes.
I have 30 minutes? Oh my God. Okay. So yeah, it looks so weird that I don't have time. Okay. Okay, sorry. So I'll go slower. So I guess I can elaborate. There's no security proof for Aronson construction for these point functions, and I view it as one of the major open problems in this field to come up with new constructions which are either provable or for larger sets of larger classes of functions, especially like all function would be great. Okay. So the last, another interesting extension is called quantum tokens for digital signatures by Shalev Ben David and myself. So the setting is as follows. Imagine you go on vacation and want to delegate the ability to digitally sign one and only one message to your friend. Now, of course, you could give your friend the digital signature's secret key, but then, of course, your friend will be able to sign as many messages as he wants, and even more, perhaps another problem is, imagine that your friend's computer gets hacked. You have no way of knowing it, right? So I'll explain how to construct such a scheme using Aronson Cristiano's ideas. And for this talk, we'll assume that you want to sign 1-bit messages. Okay? So you use a signature scheme based on this quantum money. So you generate this token A, and to sign the message 0, the friend measures the state in the standard basis. So recall this is just this uniform superposition over all the elements of A. So your friend will measure one element of that subspace. And to sign the message 1, the friend will measure in the Hadamard basis and get an element of A dual. As we've seen, applying Hadamard transform onto that state gives you the A dual, like a uniform superposition over A dual. And our main theorem is that given A and the public key, it is hard to forge two signatures. Both, like, forging signatures means finding both an element of A and a non-trivial element from A dual. Okay. So the last idea that I want to talk about is dispensable backdoors. So the motivation they gave is the following. So government wants cellular manufacturers or other hardware devices to have backdoors. One very interesting example, you can look it up in Wikipedia, was the FBI-Apple encryption dispute, which made a huge impact in the US, and eventually the FBI didn't get what it wants. And the arguments against backdoors is that one argument is that it provides too much power to the government, right? It can basically break all our devices. And another practical issue is that if this backdoor is leaked, and this often happens, information tends to leak, the bad guys can use it and break all of our devices, right? So what they proposed is to use the concept of the dispensable backdoors supplied by the manufacturers to the government, where each dispensable backdoor can be used to unlock only one device of the government's choice. So imagine if the government gets 10 dispensable tokens, it can choose, which 10, people they want to hack to, and then unlock their devices. And the underlying construction is using this tokens for digital signatures, which I mentioned before. And the idea is that in order to unlock a device, you need to sign a message containing the device's ID, right? And if you have 10 signing tokens, you can only sign 10 messages and therefore only unlock 10 devices. So some of the advantages, it kind of, gives limited power to the government, right? And limited damage if the government's dispensable backdoors are stolen, right? If someone managed to grab them. And the disadvantages is that now manufacturers have too much power. There's no way to know whether they gave only that amount of dispensable backdoors to the government, or perhaps they kept some to themselves. So the manufacturers can unlock all the devices that they want. And now another more, I guess, delicate issue is, of course, users may prefer to avoid the scheme with a backdoor. And the only way to make this plausible is if governments force people to use this kind of crypto, crypto with backdoors. And this raised me, I want to move on to the next, which is, I guess, only, I'm not sure how related this is to the main subject of my talk, but I think it needs to be discussed. So regarding our ethical responsibilities. So in general, politics is about the division of power, right? And cryptography has changed and will change the division of power. And these days, for example, end-to-end encryption is a common practice. And it means that individuals can keep their information private even against extremely powerful entities. So we should ask ourselves, in our work, are we transferring power from organizations or governments to the individuals, or are we moving power the other way, from individuals to these governments? And at least be aware that we are not neutral regarding these questions, right? We have power and we're using it one way or the other. And we can choose what we do and where we work, etc. So to give a very concrete example, this is just a photo I took from one of the industry booths here. I really don't want to make a fuss about who this specific company is, but I do want to emphasize, let's look at who are the target, people that will use this. This is aimed, these products are aimed for the government, the finance, the energy, military, emerging industries, supposed to serve national security, etc. And I wish it was a bit like more that at least maybe not the first, but that Alice and Bob from our talks should be there, right? That we should aim our thought and we should serve the individuals and not the organizations, right? This is I guess I want to stress, like, quantum cryptography is a privacy-enabling technology, and we should ask ourselves: are we using it to give more power to the organizations or more power to the individuals? And certainly, I know where I want to put my efforts, but you should ask yourself these questions and think about it and decide how you're using your power. Okay, so now, how much time do I have? 20 minutes. Good. So I have quite a few open problems which I'd like to raise. So some of them were already mentioned. So experimental demonstration of private quantum money, including storage, and another interesting aspect is experimental demonstration of public quantum money. And the Arnson-Cristiano scheme that I mentioned has this neat feature that the quantum money state is a stabilizer state, so it can be generated using the Clifford gates. And so in other words, it does not require a universal quantum computer. So if anyone here has a setup in which you can easily prepare Clifford, if you can apply Clifford gates, then you can do it easily. Another open question is whether there are anonymous public quantum coins. None of the construction achieved this, and perhaps even impossibility result, I don't know. Is the security, are the security definitions that we have are strong enough? So already, I guess, there were quite a few suggestions to how to even strengthen these and this should be considered. In my previous talk yesterday, I talked about Bitcoin, and Bitcoin has lots and lots and lots of downsides. I'll name a few. The security model is awfully complicated. You have these miners who can do various things, and you have this ledger which can only support, I don't know, 3 transactions per second, and there are lots and lots of downsides to that. And quantum money, on the other side, from a cryptographic perspective, it's a very, simple object which is easy to argue about, and so you might wonder whether there is a way to upgrade Bitcoin in some sense to quantum money. So that's it. So another open question is provably secure public quantum money from standard assumptions. Basically, by that I mean, I/O is a general assumption, or indistinguishability of obfuscation. I'll say a few words about indistinguishability of obfuscation. First of all, this is like something that made a revolution in like modern, theoretical at least, cryptography. I have a few words, so I'll try to explain what it is. So, in general, obfuscation is a compiler which takes a program and outputs another program that has the same functionality, meaning you can run the original program, but it is unintelligible in some way. So I won't explain how this is, what's the precise security definition in I/O, but I'll give you one very good example for what it can achieve, and specifically what I/O can achieve in indistinguishability obfuscation. So imagine that you have like a big company and you want to have one public key, right? And now, if you receive a message, like, who do you give this secret key to? Do you give it to all the employees in your company? This sounds silly, right? So there's something called functional encryption. What is functional encryption? Imagine that you want to give, if the message contained the word money, then the accountant should be able to open that. If it contains the word marketing, your marketing guys should be able to decrypt the message, etc. So how would you do it? So basically, imagine that you have the program, the following program, like decrypt the message. If it contains the word money, output the message. Else, output, you cannot read this message, right? And then use obfuscation to obfuscate this program. It turns out that this is secure, meaning you cannot, given this obfuscated program, of course, this program contains the secret key, right? This program contains the word decrypt using the secret key, the message. So of course it contains the secret key, but yet you cannot, there's a way to construct it in such a way that you cannot, take this secret key away, even though you have access to this program. So that's example for why it is so useful, and I think it's useful in various other cases. Also in quantum crypto. But the downside for this is highly debatable. I mean, there are no good security proofs, and we are not sure whether this is even possible. And therefore, it would be nice if we had public quantum money without this assumption, and the only one we have now is based on this. Okay. So as I mentioned, constructions of copy protecting programs for other than point functions, and perhaps more importantly, new applications for it. What can it do? And perhaps I'll give one example for such an applications is quantum tokens for other tasks. So this is revocable decryption tokens. So imagine here you go on vacation and want your friend to be able to decrypt messages now. So here, imagine that you take your decryption program and use quantum copy protection for it. And then when your friend comes back, you check that, of course, while you're away, your friend will be able to decrypt your messages. And when you're back, you check that you ask your friend to give it back. You check that it works. And then you're sure that your friend will not be able to, loses access to to the decryption function, which is, I think, very nice. Although I didn't prove security, and I'm not sure whether how easy it is to prove. One last application is called an atomic swap. So imagine that you want to change dollars to RMB. Okay. So when you change, someone moves first, right? Someone gives the dollars and gets the RMB, or vice versa, right? So either a way to do it in a trustless manner, right? That even if any of the parties cheat, you still get your coins back. Yeah, it sounds hard, right? Perhaps implausible. So prove that it is impossible. But I'll try to give a plausibility argument based on coin flipping. So let me remind you what coin flipping is. Coin flipping, you have two parties which do not trust each other, and they want to flip a coin over the phone. So using a protocol. So in the classically, this is impossible to achieve in the information theoretic setting, and quantum, there is a quantum algorithm that for coin flipping, for weak coin flipping with arbitrarily small bias, but I'll try to give the intuition. So suppose these two parties share an EPR pair, 0, 1 plus 1, 0. Okay? So if they did that, it would be extremely simple, right? They would simply measure it, and the one who gets 0 loses, and the other wins, right? And they'll agree on the outcome. They'll both get, like, the outcome will be fine. So one way to view these quantum coin flipping is they start with the 0, 0 state, and they both kind of try to affect the weights, but in a way that if one is honest and the other is dishonest, the cheating party cannot affect the weights too much. And you can think of it as what we want here is to start with dollar state and RMB state, and to move to dollar RMB plus RMB dollar, right? And then if we'll measure it, one of us will have a dollar and the other will have an RMB, right? So I'm not sure, perhaps this is a flawed argument and perhaps this is impossible. So come on, I mean, okay, sure, give me an impossibility result, I would be extremely happy. And that's it. Thank you.
thank you very much for this tutorial. Let's have a discussion, questions, etc.
Should lifetime?
Okay.
Hi.
Hello. Yeah, thank you for the talk. At some point you mentioned some signature that you could use only one to sign a message, and it looks a bit like a one-way program, and I thought that it was impossible to do, if I'm not wrong, and Brunbed needs some impossibility result about this, so what's the link between these two programs? And
So I'm not claiming I can do it for any, certainly there's no way to do any kind of program. I guess the intuition here is that the verifier gets something classical. You're sure that the verifier gets something classical, and therefore this you have to measure that state. And because you measure that state, something bad happened, and you cannot reuse it in some sense. But I'll have to think about it to give you a better answer.
Okay. Should lifetime or coherence time of quantum money be included in definition? Like, do we want quantum money to be long-lived, or is it fine if it is like just for short span of time? And is coherence more like some physical phenomenon, or do you think it is experimental issue? Like, we can have some countermeasure against coherence of quantum state?
Okay, I'm not sure I understood all of your question. Perhaps I'll answer then. If I didn't answer correctly, please ask again. So, if I understood, you're asking whether it's something physical or not. Then I don't know. It could be various things. It could be stored in our cell phones, or it could be probably it requires quantum memory. So it's going to be something very. It would require electricity, etc. It won't be like on a piece of paper. And can you?
Okay. So my question is. So in quantum money, we use quantum state, right? So,
yes.
But like we know, and there are superposition states, and due to coherence, they may change with time. So do we have to introduce like lifetime of quantum money in definition itself? Like, do we want quantum money to be long-lived?
Yeah, I guess certainly we would like that. Like one of the functions of money is called store of value. So you want it to be, you want it to be predictable how much it will be valued in like a year or so. So yeah, it's certainly something we wish to have. So you need a long-term quantum memory or a long-term quantum computer that can, store things for years. And indeed, it's an extremely hard task from an experimental perspective. Perhaps one of these questions is like, can you use a quantum public scheme which does not require a universal quantum computer, and perhaps that would make the task somewhat easier. I don't know.
Thank you.
Yes.
I think that what you're calling public quantum money was introduced by this old paper of us with Breitbart and Wiesner in 1982, except it's so long ago that we're trying to remember what it said. But we called it unforgeable subway tokens, which could be used, but recognized even by an apparatus whose workings were known by the adversary.
But if I remember correctly, the main difference there is that the bank gives different public, in some sense, keys to different branches, and the same key and it's not secret. No, okay, we can discuss it. I mean, I understood differently.
Remind ourselves of how it works. It would be broken by a quantum computer, but many of these other things would be also.
No. I mean, these schemes are supposed to be secure against quantum computing. That's one of the points of the.
Right. I remember a bit better because I just read the paper. But no, indeed, this 1982 paper in the Proceedings of Crypto-82, which was the first time that the words quantum cryptography appeared. In that paper, the whole point was to start from Wiesner's quantum money, which is private quantum money, and start from his idea and build public quantum money from it. That was the whole point. Now, the way we did that, there was the verification procedure was not secret. Anybody could verify, but only you needed a secret to make the quantum money, which we actually called subway tokens. And it turns out that the way that we had defined it, to break the system, all you had to do is factor a big number. So of course it's not secure against quantum computers. It was not built on general cryptographic assumption. It was specifically factoring. But the product of these two primes, just like RSA, the product of two primes was a public verification key. Anybody who had this public key could verify any subway token destructively.
Why is it destructive? Like if you have a quantum computer?
The way that we had defined it was destructive. The process by which anybody could verify a token was destructive. You just look at the paper, you see it.
Yeah,
sure. But to create a valid token, you needed to have provably. Contrary to RSA, here there's a proof. The only way to create a valid token would be to know the factor of this number.
Okay, so I guess my comment is that you're saying that this would work if our RSA was if you cannot factor numbers.
No, it was not based on RSA. It was not based on RSA. It was based on quadratic residuosity things, but it was based on factoring, not R.
Sure, but I mean my point is that you're saying that you assume that like the measurement was destructive, but I'm saying that like if you remember there was an attack that like by Farhi et al. I'm trying to go to that slide, and this can break any public quantum money scheme which is tensor product state. So even if you couldn't if you don't have a universal quantum computer, still you can break it. So yeah, I was kind of baffled by that paper, and but in any case, it's
no. Of course, in these old days, we didn't prove security.
Yeah.
So maybe it is not insecure because of this general paper.
Yeah.
But our purpose was that.
Sure. Okay. Good.
To have this purely public verification scheme, and again, the honest verification procedure is destructive, but there might be one that is more subtle and does something else.
Yeah. Okay.
I have a question, if I may. In conventional cryptography, it's common to look for building blocks like oblivious transfer, bit commitment, on which we can build larger protocols. So do you think that quantum money is a building block, or is there something else waiting to be discovered that would be a building block related to these concepts?
So I don't really know. My feeling is that it should be, from one-way functions. I don't see any. I think you only need, basically, one-way function imply digital signatures, and that's basically all you need. Like, but I don't have very good intuition for this, and I'm not sure. Like, but certainly we have, based on one-way functions plus I/O, we already have quantum money. But yeah, and maybe I'll even give a more detailed answer. So. Again, Mark Jandry introduced a notion which he called subspace hiding obfuscation, which is a much simpler goal than indistinguishability obfuscation. And he simply showed that I/O implies subspace hiding obfuscation, and then he uses subspace hiding obfuscation to prove security. Basically, if you can come up with a new constructions for subspace hiding obfuscation, say from, I don't know, one-way functions or trapdoor functions or whatever, we're done. I think Mark's paper gives a pretty good direction to where to look at.
Any other questions? Okay, if not, let's thank our speaker again.